Hello everyone, good morning. I am Siddhesh Tirodkar and today I am going to share my PhD research, a modeling study on ocean energetics and sensitivity of vertical mixing scheme for a regional domain in Indian Ocean. I completed my PhD under Professor Sridhar Balasubramanian and Professor Manas Ranjan Behra. Ocean is one of the crucial component of Earth and climate system. Ocean has high heat capacity and slow response rate. Ocean surface temperature is not uniform over the globe. It has cooling signature in few regions whereas warming signature in other regions. This cooling and warming patterns with other features shows the signature of different global events like the ENSO, IOD, Atlantic Nino, and literature suggests that number of such events in specific period affect the global warming. So to understand these local and regional processes, it is important to understand the ocean dynamics of the regional processes. Here we can clearly see these processes occurs on a very large spatial and temporal scale. This bottom figure shows the ocean eddies which are available at a very small scale, but they also alters the nutrient transport in ocean. So to understand the regional ocean dynamics, it is important we understand the energetics aspect of the regional ocean. So to do that, I considered the regional domain of Indian Ocean, and in that particularly I focused my research in Bay of Bengal. I selected Bay of Bengal because of few reasons, like it has warmer SST compared to other parts of Indian Ocean. It has semi-annually reversing wind system which alters the surface circulations. The monsoon and climate in the vicinity of Bay of Bengal is largely affected by the dynamics of the Bay of Bengal, and river runoff from various tributaries during the monsoon period is larger compared to any other basin in Bay of Bengal. So my PhD objectives were to undertake a regional modeling approach to understand the Indian Ocean mesoscale processes and surface and subsurface mixing in Indian Ocean. The second objective was to do the energetic study of various turbulent fluxes governing the regional dynamics. The third objective was to implement more physics based vertical mixing scheme like K epsilon mixing scheme to understand the difference between the KPP, that is the parameterization based mixing scheme, versus K epsilon, that is the more physics based vertical mixing scheme. And my fourth objective was to do the flux comparison of these two mixing scheme to understand which scheme performs better and why. To do that, first I considered the horizontal resolution of 0.1 to understand the mesoscale processes in regional domain. Here I considered the data from 2003 to 12, and the spin-up was made for the 10 years. The interannual run for the output was considered from the year 2003 to 2008. As I am going to understand the dynamics on a seasonal scale, I considered my output into 4 different seasons, that is DJF, that is winter monsoon, MAM summer, JJS summer monsoon, and ON post monsoon. So to understand the energetics, let's first discuss the energy budget equation. So in energy budget we have 5 different terms. First is the rate of change of eddy kinetic energy, second is the transport of energy, third is the production of energy, fourth is buoyancy, and fifth is dissipation. Here I want to mention that all the calculations I made are with respect to the fluctuating component. So this is a eddy kinetic energy budget equation, and the mean kinetic energy may differ from this. So if we consider the profile of eddy kinetic energy in 4 different seasons, we can clearly see that the eddy kinetic energy is showing the strong signatures near the equator due to the stronger equatorial currents, and it shows the presence of EICC in ON and MAM season. So it is able to capture the basin scale features like EICC, the strong equatorial currents, very nicely in this particular domain. If we consider the other term, that is the production flux term, So first I want to explain you what is production flux. If the production flux is positive, then we say that the energy is going to transfer from large scale to small scale. So it is going to disappear. But what if my production flux is negative? In that scenario, my small scale eddies are going to re-energize, and they are going to re-energize the mean flow and going to sustain for a longer period of time. So if we see the seasonal patterns of this production flux in Bay of Bengal, we can clearly see that in most of the domain we can easily able to see the negative production flux, which means in Bay of Bengal domain inverse energy cascade is happening. If we see the dissipation rate, we can again see that it is higher, the dissipation rate is higher near the equator in the winter monsoon and post monsoon seasons. But if we consider the buoyancy flux, the buoyancy flux is positive, which means my vertical stratification is going to be stable. If my vertical stratification is stable, then there are less chances that turbulence can occur. But if my vertical stratification is unstable, that is my buoyancy flux is negative, then the turbulence can easily happen in the surface and subsurface zones. So from this buoyancy flux, we can say in Bay of Bengal the turbulence is also because of the negative buoyancy flux. If we consider the first equation, and if we say we apply the stationary condition, then that equation is going to get transferred into production minus buoyancy minus dissipation equal to the net non-zero transport. So the seasonal pattern of this net non-zero transport shows that in Bay of Bengal the energy is getting transferred from equator to the pole. In the second objective part of my PhD, I have considered the domain with a horizontal resolution of 0.25 because of the serial processing limitation. So in this I have used two mixing scheme. One is KPP, which is mainly used by most of the ocean models, K profile parameterization, and the other is K epsilon mixing scheme, which is a physics based mixing scheme. Here it resolves two different equations, the two PDE, to find the eddy kinetic energy and dissipation, and then that the TKE and the dissipation is transferred over the domain. So it is observed from the output analysis of KPP and K epsilon that the sea surface salinity and ocean currents do not show much change with change in mixing scheme. But if we see the temperature, sea surface temperature, we can clearly see that my temperature profiles are showing lesser bias compared to the KPP mixing scheme. So to understand that whether it is a real phenomena or some false signature, we studied the vertical profile of the temperature, and it is observed that the false cooling which was happening in KPP mixing scheme is not observed in the K epsilon mixing scheme. So this mixing scheme is changing the calculation in vertical direction as well. So because of that, we can say that the sea surface temperature shows the lesser bias. But what exactly happening behind this? To understand that, I made the study of energetics, and the energetics comparison of these two outputs from the KPP mixing scheme and K epsilon mixing scheme shows that the eddy kinetic energy is not changing with change in mixing scheme. But when we studied the the epsilon, that is the dissipation, it is seen that the dissipation is lower compared to KPP in K epsilon mixing scheme. Then what might be preventing this dissipation to be slower? To understand that, we also studied the buoyancy flux, and we found that the buoyancy flux in K epsilon is slightly better compared to the KPP mixing scheme. So we can see in this particular plot that it is negative. So KPP minus K epsilon is negative, and hence this higher buoyancy is preventing the dissipation to work faster, and then my temperature, the false cooling is not visible, and that is how it is correcting the prediction of the ocean model. So the research contribution from my work is that the OBC implementation is done well. The energetics quantification provides a pathway of how the energy is generated, transported, and dissipated in different regions of the domain at different spatiotemporal scale. And the third research contribution from my work is the comparative study of two vertical mixing scheme that shows the importance of physics-based mixing scheme. These are my publications. Like I have one of the work is published in Earth and Space Sciences, and other one is published in ISS Journal of Hydraulic Engineering. Thank you.